Today we will talk about XRF analysis in the feed, also agricultural industry. Moreover, we will focus on the fast and easy analysis of macro and micro mineral nutritions in feed supplements, and similar materials. Here's a little bit of an outline of today's presentation. So first of all, we'll start with some basics. Then we'll talk a bit about the benefits of XRF and where to apply them in feed and agriculture. We'll talk about the importance of sample preparation. This will be a bit a topic throughout this talk about when and where to use which preparation technology. And we will provide application examples coming from raw material up to the final feed. And finally, we'll have a summary where you will also have the opportunity to ask questions. Let's get started. And for those who are not familiar with XRF, basically what we are doing, we have an X-ray tube that then generates X-ray photons. These photons hit the sample, they excite the sample. What does it mean? We are ejecting an inner shell electron from the atoms within the sample, and an outer shell electron falls into the vacancy. This emits an X-ray photon, a fluorescence photon if you want so. And this photon has a characteristic energy and a characteristic wavelength, as well as the number of photons ejected are proportional to the number of atoms in the sample. So we make use of this by basically in an energy dispersive system. Here you see the beam path on the right-hand side. We make use of this by using a solid silicon drift detector, essentially, and this allows us to detect both the energy of the incoming photons and count the photons at the same time, and therefore generate a spectrum of the entire sample and use this information to get the elemental concentrations within the sample. Where do you apply XRF, broadly speaking, in feed and agriculture? Essentially, almost everywhere. So you can analyze grains, whole grains, and ground samples. You can analyze oil seeds, ground as well as pellets, and as seeds themselves. You can analyze vegetables, protein, ground material, and you can analyze feed and mixes and forages. Broadly speaking, with XRF, we can cover elements from typically fluorine up to uranium within feed and agricultural applications. And we can do this and detect micro, macro, as well as trace elements, so trace element contaminants. So we're talking about ppm or microgram per gram, sometimes even sub-ppm level, up to 100%. It's actually an advantage here. We can cover this in one calibration, so the low concentrations as well as the high concentrations. Time to result matters a bit depends a bit on the application you're doing, the number of elements you're using, and the equipment you're using. There's different types of equipment out there, but typically we're talking about 3 to 15 minutes, mostly like 5, 6, 7, 8 minutes. More traditionally used in the feed and agricultural analytics are technologies like ICP-OES or AAS. However, here we have a significant advantage when we look into detail for XRF. So one point is considering the cost of ownership. Here in the AAS and OES, basically, we have some expensive consumables like graphite tubes in the AAS, like noble gases like the argon for ICP. We have some hazardous chemicals, so we need a laboratory environment. We need typically to dissolve the samples, and so we need a wet chemical lab. And we have, therefore, also more complicated sample preparation and sample preparation equipment. XRF, on the other hand, doesn't need hazardous consumables. You can start operating the spectrometers after very short introduction. You don't need highly trained lab technologists. You basically can operate it with a plant operator, and you don't need gases, except in some cases you need helium, but in lower amounts. So just to give you an example of what this means in terms of payback, when we are comparing a solid feed material that we are measuring on an ICP versus an XRF, and we measure this as a pressed a pellet with some binding material to make it more solid, and we'll talk a bit about what binding material this means here actually. And we talk about maybe costs for consumables here of $2,000 a year or less. But for ICP, for the gases in particular, but also some reference materials as well as other consumables, we are easily exceeding $20,000 per year. So this is significant and adds to your overall costs. Another clear benefit, and that's why I hope to show you this throughout the talk, is the ease of use. And the ease of use starts with the easy preparation. And this essentially pays back in fast overall time to results. So an XRF machine, you basically you use the grains or powder immediately, you might want to grind it or press it, and then you put it in the machine and measure it from minute 1 when you are in the lab. So you don't need to start calibrating and so on. Whereas for the ICP, you need a lot of pre-digestion, dilution, and so on before you even can get started. Of course, once everything is ready, measurements are fast, in the order of 2 minutes on the ICP. But half of the day you're consuming with preparation of the equipment and preparation of the samples. So this is a significant difference and the benefit of the XRF here. Some of you might wonder, well, is XRF safe? And the clear answer to this is yes. So we design and develop our systems with the highest safety standards. So there's no radiation leaking from the system. There's a dedicated system. Basically, there are safety circuits that intervene immediately when you would trigger with the system. So it wouldn't allow you to power up the tube when you basically open the system in any way or do any kind of fiddling with the system. So, and of course, we are therefore also compliant with the strict regulations like from the German government as well as the French government and other governments. We also offer for some specific regions which where this is of benefit for working with the local authorities. We also offer with the S2 Puma or energy dispersive system a 30 kV version, which allows easier registration with the governments. Now let's talk a little bit more in detail what are the typical applications for XRF in the quality assurance, but also quality control fields of feed production, feed industry, and agricultural business. So for once, as I mentioned at the beginning, we're talking about macro and micro mineral nutritions. We are also able to do the raw material identification. So for raw material identification, for instance, the ICP is typically overkill. So here you have a very fast response to what is coming and what quality does it have. You can monitor your production, of course. Besides the mineral nutritions like phosphorus, calcium, sodium, potassium, chlorine, and so on, you can also monitor traces like nickel or lead that might either be regulated in a certain way and have to be below certain limits, or are hinting maybe at some production issues. Maybe a nickel peak might hint or an iron peak might hint at some problems with a certain equipment, something broke up. Then, of course, we can also measure soils. Here we can look into the major elements as well as the trace elements that are important for the performance, let's say, of the soils, the quality of the soils, so the nutritions, but also into those which are coming from the fertilizer and enhancing perhaps or contaminating the soil in any way. And similarly, we can look into fertilizers. Here we can look into the active components like phosphorus and zinc, for example, and also the toxic trace components like arsenic or cadmium or even uranium. I mentioned a bit the sample preparation and that I will go a bit more into detail. So I wanted to share briefly an overview of what are the sample preparation techniques that you have in XRF. So for once, you can measure your material as loose powder or grains in a liquid cup, which we call a powder cup, which has a little foil at the bottom. Here, the advantage is clearly, well, it's the simplest you can think of. One point is you could use the same material that you typically also might be analyzing on your FT-NIR, so you just use the same material and put it to your XRF. You have some effect here, of course, when you don't grind it, of grain size. That has an effect, a negative effect on let's say, the quality of the data, and also of homogeneity. So that's why grinding, and I will show you examples, is typically very much recommended. Then you have pressed pellets. Pressed pellets are another solution where you either use the material straight away, could be dried forage, which you press into a pellet, or you grind it and then you press it into a pellet. You might add some binding material like cellulose or wax that helps the pellet to stick together, like the picture here on the right-hand side there. These are so-called pellets. These help you to, first of all, have a more homogeneous sample. This is then, of course, more reproducible, more reliable data quality, and also better accuracy. Here, this is typically a good solution for feed. I take this in advance. It also allows you to cover traces and major elements in one set. And last but not least, you have fused bead. Here you fuse with a flux it into sort of a glass bead, as shown here on the right-hand side. Advantages here, you get rid of all the matrix, and this gets you the highest accuracy and precision. But of course, you're diluting also significantly. So for the trace elements, this is typically not suitable. And for most applications in the feed and food, this would be overkill, but just for completeness. I mentioned grinding, and here's just one example. As you can imagine easily, you have these maize kernels here. When you measure them on XRF or FT-NIR, it doesn't matter. It's sort of heterogeneous. It's clearly heterogeneous before you grind it. Once you grind it, it's much more homogeneous, and then you can get a more reliable signal from your sample. So this is typically highly recommended. I also want to show you this picture here for showing to which level this differs. So this is a premix sample, and you can see on the upper left-hand side here that it looks fairly well ground. But when you take a closer look, you see that there are still some clusters around, even different color shapes. And this is okay to use, but when you have it a bit finer, a bit more homogeneous, you will see this in the data quality of your XRF results. So grinding is really an important step in most cases when you use XRF. However, when you grind samples, and well, for feed material in general, you might be worried about dust. Here, especially our S2 Puma, but all our XRF equipment in general, are very well set up. We have what we call sample care. This sample care is a multi-layer system. So, for instance, we have a reservoir that collects the dust. We have a shield that protects the detector from spillage. The reservoir is also fairly large, so you can clean it easily from the dust. We have a filter wheel that protects the X-ray tube. For other equipments, we have a specific shield that separates the vacuum side from the measurement side. So they're a multi-layer system that is really dedicated to allow high uptime and easy maintenance. Still, it's always good to clean your material and your equipment frequently to ensure a long lifetime, but I guess that's obvious. So now let's switch to some application examples for where to use XRF in particular with some actual data. So first point, as I mentioned, where XRF comes into place is raw material identification and also verification. So as in identification, I understand that we simply want to see when it's a mineral compound, so maybe it might be magnesium carbonate, so you simply want to make sure that it's magnesium carbonate and not some other kind of calcium carbonate or whatever you think you're currently receiving. So first of all, you want positive identification. So this is fairly simple with an XRF equipment when you're using what we call standardless approaches. So our XRF equipment, like the S2 Puma, so our high-performance energy dispersive system, as well as the S6 JAGUAR wavelength, benchtop wavelength dispersive system, have the option of a so-called standardless solution, which we call SmartQuant. And this SmartQuant works with an algorithm, essentially, that allows you to measure your sample with very minimal input about the sample. So basically, you would say it, well, it's a powder, and you might put into that's a mineral phase, or you might put into that it has a certain matrix, but not even that is needed, depending on how much you want to get from this information. And then you can easily get the information what kind of material you're dealing with. So here is just an example for a very simple differentiation of two types of chlorine samples, so potassium chloride versus sodium chloride. Here you can see in the spectra on the lower side here that we can easily distinguish between the two different types here. Oops. And of sodium and potassium chloride, so we have clear peaks here. And we can also define thresholds in our software. So warning levels, normal levels, or alarm levels if you want. So this is also important to know for your production process, of course. So then you have identified your samples. And if you tweak, if you know relatively much about your sample, you can even verify the quality of your sample to a good degree with a standardless solution. However, once you, of course, want to go to quality control, in most cases you would calibrate the instrument. And here I just want to walk you through one example. What we did here is we used some different pig feed samples, so that were certified reference samples, or basically round-robin samples, which have a set of 12 micro and macro nutritions being characterized, like the lighter elements, magnesium and sodium are included, but also copper and zinc on the heavier element. And you can see here a picture where we did this calibration. So we essentially prepared pressed pellets. The material was ground before. So in the same way as you would grind it on FT-NIR equipment, so you can use that ground material on FT-NIR and on the XRF. In this case, we press it into the pellet. This takes a few minutes. And then you can run it on the XY auto changer here. You can just place in this case, 8 samples there and hit run, and you have the calibration set. And here, one important point here, why did we decide to use pressed pellets? Well, the one point is that we are here also interested in the lighter elements. So let's say magnesium and sodium. Magnesium and sodium have relatively low energy characteristic wavelength photons emitted from the sample. And these get absorbed easily, that's why we measure it typically in vacuum to get the best signal from our sample. So vacuum is the most optimal measurement condition for light elements. But you also, when you measure it in a powder cup, you have a little bit of a foil. So this also reduces the counts, of course, that can be generated and detected by the detector. So here you have a list of penetration depth, essentially based on the different elements. I highlighted here magnesium, where, for instance, in a graphite or glass sample, we are talking about a few tenths of micrometer penetration. So this is all sort of similar. The graphite is sort of similar to your sample. So you're somewhere in between glass and graphite with a natural feed sample. Therefore, you want to have a smooth surface, and of course, you're benefiting from having no foil. And this is the reason why pressing the sample is advantageous. When you already grounded the feed, you can typically press it without wax. So this is also saving a little bit on costs, as mentioned before, and then it's really simple and straightforward. So once you've done this, once you've run it through, our software really allows you to easily set up this calibration. This here is a snapshot from our software Spectra Elements. On the far right, left-hand side, you can see our tree structure. It walks you through the calibration process. At some point, you're having here the calibration curves and the peaks, and you can really set the range which you want to integrate. You see an immediate response of what are the effects. Of course, you will get some training for this, but it's really fast and easy to learn to get a calibration done here. And then it looks like this for all the different animal elements here for this particular calibration. So you can see with a set of 8 samples, not a lot of effort done here. We already get a very good calibration for all the elements of interest in our sample. And I just want to show you here what this really means in precision. What we did here is we used a sample that we measured a couple times. So this means each time it was automatically unloaded from the chamber and loaded again. The vacuum was pumped down and we started measurement. And so this is really covering the full time to result in like about 7 to 8 minutes in this case. And what you see here that we really have an excellent precision of this solution of the equipment, if you want. So even for the light elements, so here for the lighter elements, we're talking about 2 to 3% relative standard deviation, while as for the medium and heavy elements, we are far below 1% typically, just to give you an example. Then, of course, once you've calibrated, you might wonder, well, what are the next steps? Is it always like that I need to look into the details of the calibration when I start? No, of course not. So basically, once you calibrate it, you have your solutions, you have push buttons, and you just operate the machine. So once you calibrate it, you're calibrated. There's no need for recalibration of the equipment. You just do QC monitoring, and then you can operate through our loader here from the XY auto changer, for instance, and basically load the samples, select the solution, put in the sample ID, and press start. And you can load them all in different types of material on the same tray, no problem. Different materials like liquids, powders, doesn't matter. You can put them there and hit start. So we come in our software with a very intuitive structure. We don't have floating windows, so everything is in one window. You have a tab structure, and we provide hints when needed to guide the user. But in a daily operation, you don't even need to worry about this because all you do, you're in the loader, you press a position, you select the solution and press start. And then in the results manager, you see the results. We have also full LIMS compatibility, so you can retrieve your results automatically and export them to a LIMS system if this is of interest. Now I want to bring another sample to the table, and this is forage analysis. We've seen now an example for a dedicated calibration for pig feed material. Easy, straightforward, few samples, lots of elements, wide range of calibration, done, ready for the QC measurement. Now what's when we want to do broader sets of material? It depends. And here's an example where it works very well. So forage, for instance. So forage is very similar in one way, but very different from another way. So the matrix from an XRF perspective is not the same, but it's similar. So here it's very important that we basically properly correct for the matrix effects if we want to have all these in one calibration. So the task here, or the challenge, was that we wanted to have a calibration for different types of forages, so silages, haylage, hay, different grain sizes of silages, as well as total mixed material. And this was a project that we did together with Kemel and Valley Analytical Services. They requested such a solution here, just FYI. So we have many elements in this kind of calibration that were requested. We want to go from the low ppm range up to weight percent. That's, as I mentioned, not really a challenge in pressed pellet, fused bead, so not so much, but for pressed pellet and loose powder, it's not so much a challenge. The only thing we wanted to do is basically grind the sample, dry the sample, and grind the sample. So essentially, we want to use the same material that we are also using on an FT-NIR, and we want to have a global calibration. And so this was the task, and basically we achieved it. So our algorithms allow us to essentially combine this material in one master calibration. In this case, we took an extra effort, so we really ran a lot of samples from different materials. And this is typically not necessary, but if you want to combine different types of forages, this is beneficial. And then you have, in this case, we ran 270 samples, and you can see that they nicely fall on a calibration curve here. And we were able to cover these 7 similar but slightly different materials. Time to result was here 7 minutes, and here you see some exemplary calibration curves for potassium, copper, and calcium. And what about the repeatability? Well, the repeatability is also really good. If you look at the numbers down there, you can see that for most elements, we are in a similar range than for the pressed pellets, so typically below a % relative, or sometimes even far below. Only main difference is sodium, and there's a very clear explanation for that. You see more than 10% relative standard deviation. We use a liquid cup with the foil. So I mentioned this at the beginning, that there you're of course losing some intensity. Doesn't yet play so much a role for magnesium, but plays a significant role for sodium. So in essence, we can say that except for sodium, when we compare a well-ground loose powder forage in this case to a pressed pellet without grinding, but decently ground pressed pellet application, we get similar kind of precision. So there are different ways to achieve the same goals. However, accuracy, of course, benefits significantly from dedicated solutions. And this is kind of scaling up from, you can start with a standardless solution, then you might have more global calibration, and dedicated calibrations, of course, give you the best representation of your process samples. So this is typically in production control, quality control. It makes sense to take a set of your production samples, reference them, do a dedicated calibration, and you're good to go. So this performance really is enjoyed by our customers. Like I said, we are working here, for instance, with Cumberland Valley Analytical Services, and they really showed that we can use the XRF and have significant advantages also versus ICP. And this is a very nice and complementary technology for the NIR process, and allows us to analyze multiple key mineral nutritions in a couple minutes. So CVAS has multiple installations of the S2 Puma over the world. One other example I wanted to bring here is quality control maize kernel. Here, obviously, the grinding would again help. We have different types of usages here, so it could be animal feed, classical. It could be also food for us, so the vegetables, flour, or starch, and could also be for the biofuel application. And depending on this, the final use, the requirements also differ, and XRF always performs here. So, for instance, when we're going to biofuel, we are typically interested in the very low ends for phosphorus, chlorine, and sulfur. And for this, we would typically use a polarized energy dispersive system. Won't go into detail here. This is our S2 polar. Or when you're looking into feed applications, the macro and micronutrients, you look into also the contaminants, then you're typically dealing with energy dispersive system, direct excitation like the S2 Puma shown here. I want to bring one more example. This is more coming from a research kind of perspective. So here, one of our clients uses the S2 Puma to understand better how fertilization impacts, let's say, the growth rate, the resistance, as well as of different types of and genetic types of maize. And what we did here is we essentially took a set of their samples to show you how to measure this material as well. Here you see on the right-hand side images, or basically on the center, this is images from a very young seedlings that were basically ground, slightly ground, I must say, dried and ground, so it's still relatively coarse, and then used secondary reference with ICP used to calibrate the instrument and then to measure a lot of samples to get an idea of the research questions here at stake, basically the growth rate, the uptake of different nutritions from the fertilizers. So what we did, we took 10 secondary standards, we calibrated for 9 elements. Concentration ranges, in this case, for the young seedlings range from ppm, upper ppm to 4 weight percent. And we asked ourselves one question, well, what should we do? We could do a loose powder, ground or coarse. We could do pressed pellet. Well, one advantage is here, they need to be dried anyway, then they are sort of fine-ish, like you see there, so relatively easy to homogenize by simply shaking the bottle. So we decided to go for a simple pressed pellet solution and adding a bit of wax for stability. So this is one option. Other option would be to grind it, depending really on the requirements. Here you can see that we get good calibration curves by simply pressing this relatively heterogeneous material into a pressed pellet. Also here peak for potassium shown with a very nice signal-to-noise ratio. And as expected, when we do a repetition test, we can see that even with unground samples, we get a very nice repeatability. Here we don't have sodium, but we have also magnesium. So this smooth surface that we're creating here really helps us to get a nice intensity and very good statistics with a very simple type of preparation and calibration. Up to now, I was always talking about results from our energy dispersive system. So where I introduced you at the beginning also the idea that you have a silicon drift detector that detects the photons and the energy of the photons at the same time, which especially has some benefits when you're looking into many elements in a sample. That is often the case for feed applications. However, there are some cases where energy dispersive systems come to a limit, and this is when wavelength dispersive come into play. And here we really introduced a new class of systems with the S6 JAGUAR, which is a benchtop wavelength dispersive system. Wavelength dispersive systems means, just to cut a long story short, you have an analyzer crystal that allows you to separate the incoming photons by their wavelengths. And this results in a much higher energy resolution, which on the one hand can help you to separate the peaks nicer and then also get a better signal-to-noise ratio. So when you need a bit more performance, this is when wavelength dispersive systems come into play. And there are also some clients who really appreciate this extra performance. And this is then coming more into play in the central laboratory requirements when you have a lot of different tasks to accomplish. You need some flexibility in here. And for most, and this is the most important point, when switching to a wavelength dispersive system makes sense when you also want to go to the relatively low concentrations of light elements. And here one point was, so they are looking into feed, TMR, forages, milk also, and urine samples. So they also want to get the feedback from cow urine to understand essentially how the different diets impact the cow's well-being and the nutritional uptake. So here you benefit from the performance features of the S6 JAGUAR, which comes with a 400-watt tube. You have different types of filters to optimize the incoming intensity. You have a vacuum seal that helps you to protect your equipment and results in low-cost operation. And one point I simply want to emphasize here is you also have a new generation of detectors. That's the Hisense XE detector with linear count rates of up to 2 million counts per second. So one of the key benefits here why in some cases it makes sense to go from wavelengths to energy dispersive to wavelength dispersive system is the light elements. And here the JAGUAR really performs because it allows you to, with the combination of high current and high voltage and the 400 watt power, to properly excite the light elements. So you are not even a factor of 2 better than 200 watt, just as an example here, but a factor of essentially 150% more performance here. So bottom line is our customers really like the XY auto changer. This is available for the Puma as well as the JAGUAR because it allows you to program multiple samples, and our customers really confirm that you can achieve the same precision and sometimes even better accuracy at lower costs than the ICTP in a shorter time. So this is really confirming the statement I had at the beginning. So now I want to close up with a summary. Very briefly speaking, XRF is really an excellent technology for fast and reliable determination, quantification of macro, micro, trace elements, mineral nutrients and feed and more in agricultural material, fertilizer and so on. Some key benefits are that we can cover a wide range of elements. We have a relatively simple and straightforward calibration. The system is easy to use, so once it's calibrated, you really push the button and run the sample, so no daily calibration necessary. You have low cost of operation as I walked you through. There are different types of equipment. I didn't go so much into detail today. Basically, you have an energy dispersive system. There's the Puma as like sort of the typical go-to instrument in our portfolio. When you need a bit more performance, you switch to the wavelength dispersive system, the S6 JAGUAR. And when you're working with liquid samples, oils for instance, then there are certain benefits of using a polarized equipment, especially for the very low concentrations of phosphorus, chlorine, and sulfur. Then we would switch to the S2 polar. Last but not least, I mentioned this a bit throughout the talk, there's really some complementary nature between FT-NIR, which we also offer, like the Tango depicted here, and XRF. So we can use the FT-NIR for the organics for an easy and simple and fast method, and same benefits apply for the XRF, which you could really have sitting next on the next table. You use the material that you just ground with an XRF for the FT-NIR, put it into the XRF. Press it or not, that's really a decision depending on some requirements as I explained today. Yeah, so with this, I'm basically through with my presentation.